An IP address is a 32-bit number for IV4. Think of it as a row of 32 light switches that can be either off 0 or on 1. Each group of 8 switches is called an octet, and we usually write the address in 4 decimal numbers, one for each octet, like 192.168.1.10. Binary example: 192 equals 110000000, 168 equals 10101000, 1 equals 0000001, 10 equals 00001010. Putting them together, you get a 32-bit string. 11000000 space 10101000 space 00000000, 1 space 00001010. A subnet mask is another 32-bit string that tells a computer which part of the IP address is the network portion and which part is the host portion. The mask has a series of 1 bits followed by 0 bits. The 1 bits say look here for the network, the 0 bits say look here for the device inside that network. For a typical mask, 255.255.255.0, the binary is 11111111 space 11111111 space 11111111 space 00000000. In simple terms, imagine a street address. The city and street name are the network, the same for every house on the street, while the house number is the host, different for each house. The mask is a ruler that tells you where the street name stops and the house number begins. Why do we split a big network into smaller pieces? Imagine a huge school cafeteria with 500 seats. If every student tries to sit anywhere, you end up with chaos. People shout over each other, food gets wasted, and the staff cannot keep track of who is where. Subnetting is like putting the cafeteria into smaller tables of 20 seats each. Each table has its own nameplate, so the waiter knows exactly where to deliver the food and the students can chat without disturbing other tables. The benefits are efficiency. Only the devices that really need to talk to each other share the same broadcast traffic, so the noise is reduced. Scalability. When the school grows, you simply add more tables, subnets, instead of rebuilding the whole cafeteria. Security. You can decide which tables are allowed to talk to each other, just like putting a fence around certain groups of students. Better address use. Instead of giving every student a unique seat in a gigantic hall, many seats would stay empty. You allocate just enough seats for each class, leaving the rest for future classes. Mathematically, if you have a /24 network, 255.255.255.0, you have 2 to the power of 8 equals 256 addresses. After subtracting the network and broadcast address, you get 254 usable hosts. If you need only 30 devices, you can create a /27 subnet, 32 addresses, 30 usable, and save the remaining addresses for other groups. Scenario: you have been given the network 192.168.10.0/24, and you need 4 subnets each able to hold at least 50 hosts. Find the host bits needed. 2 to the n-2 greater than or equal to 50 leads to n equals 6, because 2 to the 6 equals 64, 64 minus 2 equals 62 usable hosts. Borrow bits from the host part. A /24 network has 8 host bits. You need 6 for hosts, so you borrow 2 bits for subnets. New prefix length: 24 plus 2 equals /26. The new mask in binary is 11111111, repeated 3 times followed by 11000000, which in dotted form is 255.255.255.192. Calculate subnets. Each subnet size equals 2 to the 6 equals 64 addresses. Subnet 0, 192.168.10.0 to 192.168.10.63. Subnet 1, 192.168.10.64 to 192.168.10.127. Subnet 2, 192.168.10.128 to 192.168.10.191. Subnet 3, 192.168.10.192 to 192.168.10.255. Host allocation. In each subnet, the first address is the network address not usable for a device, and the last is the broadcast address also not usable. Therefore, each subnet provides 62 usable host addresses, more than 50 required. Mathematical view. Total addresses per subnet equals 2 to the power of 32 minus prefix, equals 2 to the power of 32 minus 26 equals 2 to the 6 equals 64. Usable hosts equals 2 to the power of 32 minus prefix minus 2 equals 64 minus 2 equals 62. The process is the same for any size. Decide how many hosts you need, find the smallest power of 2 that fits, subtract 2 for network broadcast, then borrow the necessary bits from the host portion to create the new mask. Explanation: once you have a subnet, you can always pick out 4 important numbers. Network address, the very first IP in the range, all host bits are 0. It tells you which subnet you are in. First host, the next address after the network address. Host bits equals 00000001. Last host, the address just before the broadcast address. Host bits equal 11111110. Broadcast address, the very last IP in the range, all host bits are 1. It is used to send a message to every device on that subnet. Example: using the subnet 192.168.10.64/26, mask 255.255.255.192. Binary of the mask: 11111111, 11111111, 11111111, 11000000. Network part equals the first 26 bits. Host part equals the last 6 bits. Network address: binary 01000000, decimal 64, host bits equals 000000. First host, binary 01000001, decimal 65, host bits equals 000001. Last host, binary 0111 space 11110, decimal 126, host bits equal 111110. Broadcast, binary 0111 space 11111, decimal 127, host bits equal 111111. You can always get these numbers by network equals IP and mask bitwise, and broadcast equals network or inverse of mask. First host equals network plus 1. Last host equals broadcast minus 1. Think of a street. The network address is the street name, the broadcast address is the house at the very end of the street, and the first and last host are the first and last actual homes where people live. Variable length subnet masking, VLSM, lets you use different sized subnets inside the same larger network. Just like cutting a cake into pieces of different sizes based on how many people need each slice. Start with a big pool. Suppose you own 10.0.0.0/24, 256 addresses. List the groups and their size needs. HR department 50 hosts, finance 30 hosts, IT lab 10 hosts, guest Wi-Fi 5 hosts. Sort the list from biggest to smallest, helps avoid waste. Allocate the first largest subnet. Need greater than or equal to 50, so the smallest power of 2 is 64, 2 to the 6th. Prefix equals 32 minus 6 equals /26. Subnet A 10.0.0.0/26 addresses 0 to 63. Usable host 62. Allocate next subnet. Need greater than or equal to 30, so 32 addresses 2 to the 5th. Prefix equals /27. Subnet B 10.0.0.64/27 addresses 64 to 95. Usable hosts 30. Next, need greater than or equal to 10, so 16 addresses 2 to the 4th. Prefix equals /28. Subnet C 10.0.0.96/28 addresses 96 to 111. Usable hosts 14. Lastly, need greater than or equal to 5, so 8 addresses 2 to the 3rd. Prefix equals /29. Subnet D 10.0.0.112/29 addresses 112 to 119. Usable host 6. Remaining addresses 10.0.0.120 to 255 are still free for future use. Why VLSM matters. Without VLSM, you would have to give every department the same size subnet, say /24, wasting most of the addresses. VLSM lets you match the subnet size to the actual need, saving address space and simplifying routing because each subnet has its own mask. Analogy: imagine a bookshelf with compartments of different lengths. Bigger books, HR, need a large compartment, tiny picture books, guest Wi-Fi need only a small slot. VLSM is the planner that decides how to cut the shelves so nothing is left empty. Mathematically, for each requirement h you find n such that 2 to the n minus 2 is greater than or equal to h, then prefix equals 32 minus n. Classless inter-domain routing, abbreviated CIDR, replaces the old class-based system, class A, class B, class C, with a flexible /prefix notation. Supernetting is the opposite of subnetting. You combine several smaller networks into one larger block to make routing tables smaller. How summarization works. Suppose a router has to know routes to 4 networks: 172.16.0.0/24, 172.16.1.0/24, 172.16.2.0/24, 172.16.3.0/24. In a classful world, each would be advertised individually, so the router's table would have 4 entries. Look at the binary of the network part, first 24 bits. 172.16.0.0 equals 10101100 space 000, 1000 space 000000000 space 00 space 0000000. 172.16.1.0 equals 10101100 space 000, 1000 space 000000000 space 00 space 0, 10000. 172.16.2.0 equals 10101100 space 000, 1000 space 000000000 space 00 space 1000000. 172.16.3.0 equals 10101100 space 000, 1000 space 000000000 space 00 space 11000. The first 22 bits are identical for all 4, the part up to the bolded bits. Therefore, we can represent all 4 with a single supernet, 172.16.0.0/22. The new mask is 255.255.252.0. Binary 11111111 space 11111111 space 11111100 space 000000000, which covers addresses from 172.16.0.0 up to 172.16.3.255. Benefits: fewer routes, the internet routing table stays manageable. Faster lookup, routers match a longer prefix first, then fall back. A summarized route reduces the number of comparisons. Mathematical view. Number of /24 networks inside a /22 equals 2 to the power of 24 minus 22, which is 2 squared equals 4. General formula. If you have n contiguous /x networks, you can summarize them as /y, where y equals x minus log base 2 of n. Analogy: think of a library index. Instead of listing every single book titled Science under its own card, you put one card that says all science books from shelf 1 to 4. The librarian, which is the router, finds the book faster because there are fewer cards to scan. Explanation: when you design a real network, you follow a planning checklist, use calculators or software, and verify the results. Planning steps. 1. Gather requirements. Number of devices per floor, future growth, security zones. 2. Choose address range. Often a private block like 10.0.0.0/8 or 192.168.0.0/16. 3. Draw a diagram. Sketch routers, switches, VLANs, and where each subnet will live. 4. Calculate subnets. Use the step-by-step method, see topic 3, or a tool. 5. Validate. Ping check that no 2 subnets overlap, confirm broadcast domains are correct. Tools. Online calculators, e.g. subnetcalculator.com, let you input a base network and required hosts, then print masks, ranges, and broadcast addresses. Command line utilities, ipcalc, subnetcalc on Linux, or PowerShell new object system, net IP address methods. Network design software, Cisco Packet Tracer GNS3 or Visio for diagrams. Real-world scenario. A mid-size company has 3 floors, required host counts. Floor 1, 120 workstations. Floor 2, 80 workstations. Floor 3, 30 workstations. A solution. Start with 10.0.0.0/24 22-1024 addresses plenty of room. Allocate subnets using VLSM. Floor 1 needs greater than or equal to 120. 2 to the power of 7 minus 2 equals 126. /25 mask 255.255.255.128. 10.0.0.0/25 addresses 0 to 127. Floor 2 needs greater than or equal to 80. 2 to the power of 7 minus 2 equals 126 still, but we can use /25 again or be tighter. 2 to the power of 6 minus 2 equals 62 not enough so /25 again 10.0.0.128/25. Floor 3 needs greater than or equal to 30. 2 to the power of 5 minus 2 equals 30 exact. /27 mask 255.255.255.224. 10.0.1.0/27. Remaining space 10.0.1.32 to 10.0.3.255 is kept for future labs or guest Wi-Fi. Verification. Use ipcalc 10.0.0.0/25 to see network broadcast first to last host. Ping between floors to ensure routing works and check that devices in different subnets cannot see each other unless a firewall rule permits it. Analogy: planning a city's neighborhoods. You first decide the total land area, then carve out districts sized for the expected population. You draw a map, assign zip codes, subnets, and later you can easily deliver mail route packets because the zones are clearly defined. Tip: always leave a buffer of at least 10 to 20% of addresses for unexpected devices or growth. This avoids resubnetting later. IPv6 uses 128-bit addresses written as 8 groups of 4 hexadecimal digits, for example 20010db, 885A30000000, 8A2E03707334. The large size means we never run out of addresses, but we still need to divide them into sub-networks. Prefix notation works the same way as IPv4 ID R2001db 8/48. Means the first 48 bits are the network part, the remaining 80 bits are for subnets and hosts. Why /48? An ISP usually hands you a /48 giving you 2 to the power of 128 minus 48 equals 2 to the power of 80 possible addresses, more than enough for every device you could imagine. Step 1. Decide the subnet size. Common practice is to use /64 for each LAN, because many IPv6 features like SLAAC require a /64. Step 2. Calculate how many /64s fit in your allocation number of subnets. Equals 2 to the power of new prefix minus original prefix. Example: from a /48 to /64, you have 2 to the power of 64 minus 48. Equals 2 to the power of 16 equals 65,536 possible /64 subnets. Step 3. Create a subnet. Take the first /64 as 2001db, AdaBCD0000 /64, the next as 2001db, AdaBCD0001 /64, and so on. Host addressing within a /64, the lower 64 bits are for the interface identifier IID. The usual method is to let the device generate its own IID using the MAC address EUI64 or privacy extensions random IDs that change over time. Analogy: think of an IPv6 address as a huge library's catalog. Number: the first part prefix tells you which building the book belongs to, the next part subnet tells you which floor, and the final part host tells you the exact shelf and position. Because the library is enormous, you have plenty of floors and shelves for every possible book. Example calculation given: 20010db 81234/48 goal. 4 subnets for 4 departments. We need at least 4 /64s. Need 2 bits of subnetting. 2 to the power of 2 equals 4 new prefix. Equals 48 plus 2 equals /50 subnets. 20010db 812340000/50 covers 20010db 812340000. To 20010db 812343 FFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFF/500010db 8123440000/50 20010db 81234C000/50. Each of these can be further split into /64s for individual LANs. Key points always use at least a /64 for a LAN subnet sizes are powers of 2 just like IPv4 the huge address space. Lets you give every device a globally unique address without NAT planning. Follows the same logical steps decide needed subnets calculate bits to borrow write the new prefix and verify ranges. By treating the 128-bit number as a long row of light, switches the same binary math you used for IPv4 works you just have many more switches to play with.